So let's get started. We are on day one right after lunch. Carb load has hit us, and my general rule is no more than half the audience is allowed to be asleep at one point in time. So if you feel yourself nodding off, just kind of nudge the person to the right of you. So we're going to talk about data cleansing using both SQL Server and R. My name is Kevin Feasel. I'm a manager of a predictive analytics team in Durham, North Carolina. Also, I'm a data platform MVP, and I have a blog, Curated SQL. The idea behind Curated SQL is that I want to try to find and link to 5 to 10 interesting blog posts per day. So interesting here is database development, database administration, it could be security, Power BI, R, Hadoop, this broad data platform space, curatedsql.com. The general concept that I want to hit today is what is dirty data? How can we go about trying to fix some of it? There are a lot of different definitions of what dirty data is, different concepts in this space. And I want to take a couple of minutes and talk about them in some procession. Before I get into that detail, let's talk about my general philosophy. Clean the data as soon as possible. I mean, this sounds kind of anodyne. This sounds like, well, obviously this is the case, but we have data come in and it goes into a transactional system maybe, or comes into some source of record. And then if it's bad in there, it's probably going to be bad downstream as well. So maybe we can try to fix it in a warehouse. It's like the movie equivalent of we'll fix it in post-production. Sometimes that works. Sometimes, though, you don't exactly know what the correct answer is. The correct answer might have been known at the beginning, but we lost that ability when we accepted the bad data. Occasionally, we're able to clean things up down at the end when we're generating reports, when we're doing analytics. That's pretty interesting, and I'll show you some tools to help you out in this regard. But as a general principle, this is not the best place to do it because my analysis will be different from your analysis because the way that I cleanse the data will be a little different from the way that you do. Unless we follow exactly the same rules, we may get different results when trying to do the same thing. So try to fix it as soon as possible. And as mentioned, we're going to be looking at different techniques across SQL Server and R. There are plenty of tools and other techniques that I wish I could get into, but we're not going to have the time for that. And that includes things like data provenance tools. Data quality services is a mediocre to bad attempt at a solution, but it exists. There are much better solutions available as well. So we'll talk first about high-level concepts and then hit some SQL Server stuff. Item number 3, I'm going to leave as a bonus for you because bonus means I won't have time to cover it, because I want to cover R in some detail. So let's start talking high level. At the basic concept of dirty data, think about you have a title. And that could be a Mr., or Mrs., Ms., Miss, Doctor, Reverend, Captain, whatever your titles may be. Now suppose that that is a free-form text field, and so anybody can type something in. So you may have MR dot, you may have MISTER, you may have MR without the dot, you may have MRFER, which is my attempt at trying to type Mr. on my cell phone, and all of those things are supposed to represent the same concept, but when we pull it in and try to group by that title, we're going to get a whole bunch of different answers. So that's one example of dirty data. This is a data consistency problem. We have other problems like, is your data physically or logically impossible? If you have a 6-year-old with a driver's license, then that's a very interesting place to live in. Probably that's just bad data. Do you have data that you expect to be complete but isn't? Maybe you have a lot of nulls. One example of this might be that I have a group of sales associates. They have you fill out a form. And, well, you as a consumer say, I just want to consume this thing. I don't want to spend the rest of my life filling out a 15-page document telling you everything from my blood type to the name and numbers of my dogs. So I'm going to leave a lot of this stuff blank. So then the sales associate dutifully enters nothing into the form, and then you try to analyze and have a bunch of empty results. So the question would be, do we have some sort of reasonable coding that we can do for a blank value, or do we have to throw these rows away? Can we do something with this? And are these fields even vital for analysis? And if they're not, why are you asking me what my blood type is if you're not going to do anything with it? The answer, to sell it to somebody else. So data accuracy. I wish that I could make $500 million an hour. Spoilers, I don't. I don't know of anybody who does. That, if I see it on a form, is an absurd answer. It is patently wrong. What is the correct answer? I don't know. Maybe it's $500 an hour. Maybe it's $50 an hour. Maybe it's 500 million Zimbabwe dollars. That doesn't sound nearly as nice as 500 million Australian or US dollars, but this comes down to what do we do when something is just completely wrong? Or, a little bit less absurd of example, we have two source systems, and those two source systems should agree, but sometimes source system 1 says the value is 14, source system 2 says that it's 18. How do we determine which of those two values, if either, is actually correct? How do I figure out if I have duplicate results? Let's say we have a form. Somebody hit the submit button and got really impatient and hit it 5 more times. So now we have 6 rows in there. Or alternatively, maybe we had 6 people enter the exact same data and hit the submit button and we have no way of differentiating. So is this truly duplicate data? Is there some absolute uniqueness? And if so, are we taking advantage of that? This leads to some rules of thumb. If you've got impossible measures, throw them away. This is obviously bad data. If you have data that's missing null values, I keep it because it's missing, but that doesn't mean it's bad. And also, it may be interesting to see, only 2% of people are filling out their blood type. What's up with those 2% who actually are? If you have data that you know is fixable, like those various forms of MR, probably should fix those because you know what the answer was, you know what the intended answer was, and just because somebody didn't get quite to that intended answer doesn't mean that our analyses down the stream should fail as a result. But that $500 million an hour, that's a tougher call. I don't think you can just say, well, let's change it to some other value, because you don't know what that other value is. If you absolutely have to change it, typically a safe thing to do during a data analysis is I'll set it to the median of all values in the set. That way, I don't affect the aggregates, but if you have a bunch of values you're doing this to, this can lead to distortions of its own. So you may end up dropping those records from the analysis. So those are principles I'd like you to keep in mind through this talk. And we'll look at ways to try to clean up some of these problems using both SQL Server and R. The biggest, most interesting way to do it in SQL Server is something that probably you're already doing, and if so, bully for you. Keys, constraints, ways of limiting the data that can get into a system. Normalization is the first constraint. It's a logical constraint, it's not a physical one. And there are several ways to normalize a set of tables to get to an answer. But this is probably the first gate in order to protect bad data from getting through. Then we talk about data types and the actual physical constraints that exist in a relational database system. So with normalization, when in doubt, go with Boyce Codd. Boyce Codd is a general form of third normal form. There are higher forms than third, and I love me some fourth and fifth normal form, but that's not always important for most applications. It pains me. I'm having to force myself to say these words because I am such a normalization aficionado. I love the concept so much, and yet I could say it's not always that important to go up to fifth normal form. That was actually painful for me. But I have a link in case you're interested in how to find a really cool way of deriving Boyce Codd normal form from a gigantic table. So you have all of your attributes together, and then this will get you out into a set of tables that will work fine for Boyce Codd. It's a really interesting solution. So I'll show you the link at the end. And also, I'll give you a quick example of it when we get into the demo. As far as data types go, smallest data type you possibly can use, tightest data type you possibly can use. So in other words, this is numeric values, must be greater than 0. And let's say between 0 and 100 is our domain. Well, I probably don't want to use a varchar max because that's going to let anybody type in whatever they want, and there will be some troll who will come in and type in the word 70 instead of the number 70. I'm usually that troll. Something to think about. Tightest domain. You don't necessarily need an 8-byte big int for a 0 to 100 value. You could use a 1-byte tiny int. That has some benefits downstream for the database administrator who won't be chewing you out quite as much about why are you using up all of my disk space? Disks don't grow on trees, you know. I have to go buy these things. Thankfully, I'm no longer that crotchety database administrator. I'm still crotchety, I'm just no longer a database administrator. So smallest data type, best data type. When it comes to constraints, primary key constraints tell you this is a unique row. This is the thing that tells me that this is a new row. A unique key constraint is another way of saying this is a unique row. There are some minor differences in how relational systems implement primary versus unique key constraints. Let's gloss over that stuff. Basically, every one of the sets of columns that define a unique row should get their own key constraint. Pick one for the primary, all the rest will get uniques. We use foreign keys to tie together different tables. That way, if you take over a data model that has 500 tables and has 0 foreign keys, you go insane because there's a very difficult way of trying to reconcile how these things actually relate. Foreign key constraints let us get that easy reconciliation, but they also provide data cleansing in the sense that if I have a lookup value, Mr., Mrs., Ms., Miss, I can choose that lookup value, and I can ensure that this value exists in my table. So there's no way that I can get an invalid value in my table. The foreign key constraint will actively prohibit it. Check and default constraints are ways of tightening down our domain even further. So a check constraint might say, well, you can only go from 0 to 100. A tiny int has a domain of 0 to 255, but I can put in a check constraint that says that if you're over 100, then this is not valid. This is an invalid element. Default constraints say I don't need to accept a null. I can accept some value that will default to maybe a true or a false. Maybe it could default to some specific number or some specific text. All right, let's talk demo. So I have a database in here that is called Raleigh Crime. This is a set of crime data for for the city of Raleigh in North Carolina from the year 2005 through 2014. And I have this database already created, and I've got a table loaded called police. So this police table came from a CSV data set that had columns that were really helpfully named like LCR and INCNO. So we're going to work on that a little bit. We're going to normalize these tables. We're going to create some constraints. We're going to give slightly better names because I like naming things. And we're going to try to make this overall just a better data set. So let's top 100 from dbo.police, and we'll see a quick idea of what this data set looks like. LCR and LCR desk, it turns out, this is the incident code, and this is a description of that incident code. Now in this data set, every time you see this particular incident code, you are always going to see this particular incident description. This is what is known as a functional dependency. So my description is functionally dependent upon a code. These functional dependencies define how we normalize tables using Boyce Codd normal form. Because what it says is, if I have a functional dependency like I have on LCR pointing to LCR desk, or excuse me, other way around, then I need to make sure that LCR is a primary or a unique key on this table. Well, LCR cannot be a primary or unique key on the table because we have duplicates. So I have to break that out into its own table. This does not belong in the big table police. So I'm going to give it a new table that will have my key column, the LCR, and it will have my functionally dependent columns, the description here. I'll break that out. It will become a new lookup table. And I repeat this for each functional dependency that's in this data set. And that, in about 50 words, is how you get to Boyce Codd normal form. Again, the link that I have will show you a video where you walk through it in a little bit more detail. It's kind of an interesting concept. Aside from that, we have a few other data types. Incident date time. This is a string that represents a date time value. So probably should make that a date and a time. The beat. This is where a set of officers patrols in a specific area during a specific set of time. We don't have any additional information on this beat, but I could see this being a lookup table of its own. We can pretend that the Wake County Police Department is going to send us this data in a couple of weeks, but we don't have it today. Incident number is a unique identifier for a particular incident. Now, this follows the first rule of data type naming, which is that if you have number in the name, it is never numeric. So, all right, we got to deal with it. It's text. That's okay. I'll live with it. And location is geolocated. Notice that it has a precision of some ridiculous number after the decimal. In reality, this event did not happen exactly at this location. This would be approximately a molecule, given how far out we're at. The police know exactly which molecule the bullet hit. In reality, what they're doing is more of, let's say the incident is here. They're going to build an area, and they're going to pick some arbitrary point in that area. That way your analysis is still accurate on net, but it protects the privacy of everybody involved. So, all right, that's a lot of words. Let's start doing this stuff. I have a table incident code, and this is what I was talking about. This was the LCR. So these are really incident codes, and I've given them a type. So incident code has a varchar 5 and incident description of varchar 55. That's the maximum length of an incident description in my data set. I want to create a primary key constraint so that I can tie it later to a foreign key. And I'll insert all of my descriptions from the police table. And so I've already created these two tables, so I don't have to run them here. Save me about a minute. I also create an incident table. Here I've created a table with a surrogate key. There's a whole debate about whether surrogate keys are necessary, important, wise, or foolishly terrible ideas. I'm not going to get into that discussion today. I'm okay with them. I'm also okay without them. But we've created one. So this is my surrogate key, and just years and years of this being drilled into my head has me create that as the primary key and ends up being a clustered index. I also have my incident code, but I took off incident description. That lives in its own table now, so it no longer exists in my big table. I renamed incident date beat ID, changed incident number to a varchar, and made incident location a geography. I have a unique key on this incident number. I have a unique key on this incident number, and I've defined that down here. I have a foreign key on incident code, and then I've put a check constraint on beat ID. I know that the beat must be a positive value, so beat must be greater than or equal to 0. I also know that my incident date must be within a certain range. Because I pulled this data in the year 2014, I know that there shouldn't be any values that are later than 2014, because if there were, then we've got some type of a minority report precognition police thing going on. And as far as I know, Raleigh doesn't hire any of those police officers. So I insert data into the incident table. From dbo.police, let's start polling. I'm using try-parse, which was introduced in SQL Server 2012. This will allow me to specify a particular date format and say, you know what, you figure this out. I'm going to tell you that the people who put this in were using US English as their locale, and I want you to give me a date time that matches up with it. So going back to this table, you might notice that these are month, day, year instead of day, month, year. So if I change this to UK or Australian English, then I'm going to get some different results. But because I know that this was US English, then I specify and I get back the appropriate values at date time. My geography, I'm using a CLR function that's been around since SQL Server 2008 to convert a string into a point, a geographic point. So latitude and longitude pair. I run that and I now have a couple of tables. So there's this incident table and this incident code table. The incident code table, shouldn't shock you, is a couple hundred records and just shows you different incident codes. Ignore this for now, we're going to talk about it in a moment. So we have the different incident codes. If I come back to the incident table, I have incident IDs and the associated code. We've got the date, the beat, the incident number, and location. Notice that location is now binary. It's because geography types are saved as binary. And then I can use other functions to convert them back into point values. What this means is I can also say, show me all the values within a certain circle, or show me all the values that are relatively near to this point. So I've opened up the things that I can do with this data. So we skip this and start going into mapping tables, which is what I was hiding just a moment ago. See, the problem sometimes with a data set is I want to analyze data at a coarser grain than may exist in a transactional system. In the police example, I may want to take all of my types of a particular incident and convert them into a more generic form. So we'll see that there are cases where there are a bunch of different types of forgery. I don't necessarily care about that for my analysis. I just want to know, is this forgery or not? And if it is forgery, let's assign it to a forgery type. So let's do that now. I have a note in my text that sometimes I'm not able to modify the table itself. Sometimes I may have to create another table and create a many-to-many relationship with that table, where I'll create an incident type table and an incident code table and an incident code incident type, even though I know that there's only one type per code. So sometimes you have to do that because the business side says, no, we can't make changes to the original data set. Or it's a third-party vendor tool where you're not allowed to make any changes to it. In this case, I talked to the product owner, who happened to be me, and I explained to the product owner that this was a really important thing, and the product owner said, okay, go ahead and do it. So I was able to add an incident type ID. So my incident codes are going to have a type, and I've got a type table. Notice here that, I did use a surrogate in this case. I didn't need to. I could have just made it incident type. My primary key is on the ID. My unique key is on the type. So every type is unique. And then I'm going to create a foreign key constraint going back to incident code that says every record and incident code that has a value better show up in this incident type table. If it doesn't show up in the incident type table, then it's invalid. Now, I have a whole bunch of rules for mapping, and don't even worry about reading this. I'm going to show you something even better. Spoilers. So let's create a table incident type, and I'm going to switch over to use the Raleigh crime data set. I'm going to insert into the incident type table this. Let's walk through this, because I love cross-apply, but it's kind of unfamiliar to a lot of people. From the incident code table, I'm going to use the cross-apply function to chain a bunch of replace statements. Think of the cross-apply operation as, for each record, go do something. So for a developer, this makes a lot of sense intuitively, and for a database administrator or database developer, this performs well because it's a set-based operation. It's one of those cases where that procedural step-by-step and the set-based do everything at once turn out to work quite nicely together. So my first case, I'm going to replace the incident description and replace every statement that has a space and a w/ with a minus w/. Let's go take a quick look at what that means. as I mentioned, there are a bunch of cases where I have forgery, or there are a lot of different types of fraud. There's flim-flam, and then there's identity theft flim-flam. To this day, I still don't know exactly what flim-flam is, and I don't want to look it up because that would ruin my vision of what flim-flam is. But I don't care that this is flim-flam with identity theft. It's fraud. So I want to try to basically take the first interesting looking word in the description and slice it out. So forgery. All of these things are forgery. All of these things are fraud, and so on. To do this, let's replace any space W with a hyphen W. Murder, embezzlement, assault, larceny, and rape tend to are the only cases that have a space and then another word. So I replace that space with a slash. Then I now have an incident description. And by the way, you'll see that I'm chaining this so that like IDW is what I create here. And so I look at IDW's incident description and call that IDM. And I look at IDM's incident description and I call that IDE, and so on. When I'm done, I've got a final incident description. And I'm going to find the first case of a slash, of a hyphen, of an open parens, and I'm going to assign those as values. First slash, first hyphen, first parens. Then here I have a case where I say, all right, I know that char index will return 0 if that value does not exist. So if my incident description does not have an open parenthesis, it will return 0. I don't want it to return 0 because I want to get the minimum value. So I want to find the first of these characters. So let's just put that as a sentinel value way out at the end. I know I'm never going to hit 999 because my incident description length is 55 characters. So I'm never going to get there until eventually it gets to 1,024 characters and I get there. But those are problems for another day. So I've got 999 if it doesn't exist, and I've got the actual character value if it does exist. So I've got that point in the array, so to speak. Then, quick check, what's the first of these deciding characters? I'm going to take that first deciding character, and I'm going to get the substring from incident description, starting at point 1 up to, but not including, that deciding character. And I ltrim and rtrim. Or, if you're really fancy and you're using SQL Server 2017, I trim. That right there just saved me a bunch of characters. 316 rows affected, but notice that IntelliSense doesn't work for it in the version of Management Studio that I have, which is 2016. So if you want IntelliSense to work with the trim function, you have to download 2017's Management Studio. Okay, so now we have incident types, and I want to get a dense ranking of them. What that does is it will give me a unique number for each one of these incident types, and by making it a dense rank, we go from 1 to 2, and then the next value will be a 3, and so on. Otherwise, it would have gone 1, 2, 9, on and on. Dense rank is not necessary for this. It makes it look a little bit nicer. I can easily see when the next value comes up. So 316 rows. I can then insert all of these values into the incident type table. So I've got all of these incident types, 1, 2, 3, and so on. And through this, I update incident code, set the incident type ID based off of that incident type. I've been able to take this data set, winnow down to the specific rules that I want, create a new table based off of that, and then update the existing table to point to that higher level type. I'm going to use that type later on in analysis so that I can see all the cases of fraud, all the cases of murder, all the cases of embezzlement. So let's go into the R section. We've looked at handling some of this work with SQL Server. Now let's go pick out another fun language, R. This section flows from a vignette that Hadley Wickham put together. Wickham is one of the key players in the R space, and his work structuring data sets to facilitate analysis, despite having a very academic title, is a really good read. Basically, he starts from the premise that, look, you've got data sets, and data sets are made up of variables and observations. A variable in a data set is a column. An observation in a data set is a row. In relational database terminology, variables are attributes and observations are entities. All the same thing. Variables, he goes a little bit further and defines down variables a little bit more and says that these actually should measure the same underlying thing. So let's say you have a variable called height. Every observation, that thing should be a height. It should not be a height for one person and then a favorite color for another person and then tail length if it's a dog in this data set instead of a person. It should all be the same thing. Observations should contain the same set of variables for each element in the set. So, in other words, let's say we have a set of hospital visits. Every one of these things is a hospital visit, and it has the same set of variables. We have the same structure. The reason that we do this is because it's a lot easier to describe relationships between variables. In other words, to build those functional dependencies that I just glanced over. Age is a function of when you were born and what today's date is. We can tease that out a lot more easily if today's date and date of birth are two variables instead of two observations. By contrast, it's a lot easier to group data, to aggregate data across observations than it is across variables. Our tooling is built for grouping observations. So how many people are using this phone number? How many people came in on the 19th with a case of, they were presenting for tuberculosis? We can get these numbers pretty easily in either a SQL language or in R. And what Wickham ends up saying is, look, tidy data is basically third normal form. You take your data, you normalize it. I prefer Boyce Codd, but you normalize your data, and then he says, as a practical matter, you probably are going to denormalize the data back in for that R analysis, but at least at one point, this data was normalized. So he has a series of libraries that are designed to solve these problems around data cleansing. The first one that I'm going to look at is tidyr. This is just some simple functions to tidy up data. And let's take a look. I've got some Jupyter notebooks. Notebooks are also fully available. The thing that I like about these notebooks is that you can take them, and if you have Jupyter installed, you can run them yourself. So I'm going to start. Actually, let me quickly talk about what I did up here. I'm saying if you don't have this package tidyverse, then go install it and load it. If you do have it already in memory, cool. I don't need you to do anything. And I do the same thing with ggplot. Let's bump this up a little bit more. So tidyverse is a whole bunch of different libraries that are all designed to work together to cleanse data. tidyr is just one of them, and we're going to look at a couple more as well. ggplot2 is a way of mapping data. It's a way of displaying graphs. It's a way of visualizing data. I run them and I get a bunch of warning messages that say nothing of importance to us, and then we start looking at our first data set. All right, so this is a data set that was a Pew survey of people, and this is what they presented to people. We have one variable here. It's very clearly a variable, and it's religion. We have another variable that's spread out among a bunch of columns, and that is income bracket. And the numbers in between, these are the numbers of people who decided to answer a particular way on religion and income bracket. The problem is that if we want to do any type of analysis, as opposed to just looking at the chart, if we want to analyze this at all, what we really want is for this to be its own variable, so that we would have a religion variable and an income bracket variable, and then we would have a measure that would tell us how many people answered this religion, this income bracket. And we can use tidyr to do that in just a few lines of code. So I'm going to read the data from this CSV that I have. Everything eventually comes down to CSVs. And I am taking the data and I'm using a pipe operator. So this is the pipe operator in R, %, angle bracket, %. What that is saying is take this data frame, this data set, and send it to the next function. The next function here is called gather. Gather acts as an unpivot operation. So what I'm doing is I'm saying, I want you to gather and create a new column called income. And that income is going to have all of the names of the income brackets. I want a new column that's called frequency, and that's going to be the inner guts of the cross product of this religion and an income bracket. All of the columns that are needed for income are then defined afterwards. And I have a minus before religion. Basically says every column except for religion is actually part of income. So I can use minus. I can also list the columns specifically. And I do that. And now I have the data that is unpivoted. So I have frequencies, and I have religions, and I have incomes. And now I can use a tool like ggplot. And in a half dozen lines of code, what I can do is create a really ugly looking graph. In about 4 more lines of code, I can make it a much less ugly looking graph. But all I'm doing here is I'm saying, okay, take this data set that you have now and then apply it. Basically apply that data set and say the x-axis is religion, the y-axis is the number of participants who said this, and the coloration is income bracket. I could also lay it out as a heat map. I could also lay it out as some other visualization format. The rest of this is commentary. The rest of this is just adding things like labels and titles. So that's unpivoting data. It's a pretty simple example. I want to get to a slightly more complex example. And here's a data set. This is tuberculosis data. I have a couple of variables here, and then I have these things. This is males between the age of 5 and 14, males between the age of 35 and 44, females between the age of 0 and 14. What I have here is either 2 or 3 separate variables. For today, I'm going to treat it as 2 variables, male or female, and age range. And then I have some number of cases. Notice that a lot of these have NA. We don't have any samples for this particular sex and age range. Whereas here, we do have a sample and there were 0 values. So those are important to consider. All of these NAs, I don't have those samples. We can throw them out. They were only needed to pad out this grid. But we're not going to keep the grid. We're going to unpivot the data, break it out, and then get our measures appropriately. So that's what we do starting here. I take my tuberculosis data, and I pipe it to gather. So again, we unpivot the data. We take all of those values. We say, I want to create a new variable called demographic data. I want to create a new measure called N, number of participants. Then I take the set of columns that will make up demographic, and that is everything except for ISO2 and year. And by the way, let's remove all the NA values. Let's remove all of those null values because they don't really exist. They were just padding. After that, I use the separate function to crack out the particular demo value into 2 separate columns. So I do that, and I end up, by the way, I should probably note that the one parameter here, separate after the first character. So I know that there's one character, and I can break it out into 0 to 4. And as we keep going down, we have females who are undefined. And that's at the end of the data set. So overall, this was a little bit over 115,000 observations. And I can take those observations and I can plug them into a model. Maybe I say, I think that the number of cases of tuberculosis is dependent upon, it's a linear function related to year and whether you're male or female and your age range. And I can run this and I can scroll down and see all of these asterisks which say that yes, this is a really tiny p-value, and I'm going out and I'm going to publish this paper, and I'm going to get rich because that's how you do it in academia, I think. Until somebody goes and looks and says, you know that explains about 2% of your variability, right? And I say, yeah, but I got p-values. Prolonged sigh in there on purpose. So let's move on from my horrible academic career and talk about EAV, my horrible professional career. Sometimes data sets come in as entity attribute value combinations. So what we have is we have the entity itself, we have an attribute, and we have a value associated with it. In this case, we have kind of a real kicker because, first of all, you'll never guess how many number of these there are, because this is day values. This is like day 1, day 2, day 3. We're looking at weather station data, and these are the minimum and maximum temperatures for weather stations in some locations in Mexico over a multi-month period. So we have 31 of these that are all really supposed to be the same thing. It's the day of the month. We have min and max, and notice that for day 2, the min and the max are in the same column. The problem here is that if I want to do some sort of aggregation, let's say I want to get the average max in this data set, I cannot simply take the average of day 2. I have to take the average of day 2 where element is T max, and that's a lot more effort than it should be. So let's fix that up. I am going to take my data set, and in just a few lines, we're going to crack this thing. We start by taking the original data and piping it to gather. So we're unpivoting. Now previously I'd showed you unpivoting by taking every value except for the ones that we named. Here, I'm naming the values. Specifically, I'm saying every value between D1 and D31 in my data set, I want you to take all of those things and unpivot them, turn them into a column. That column will be called day, and the numeric measure that was there will be called value. Then I use another element of the tidyverse, readr, to parse the number out from that day, basically get rid of the D. So that's going to be called day, and I mutate, so I'm modifying the data set, I'm modifying that data frame, and changing D1 to 1 and making it numeric. Then I want to select only the relevant fields, so I use the select function. Then I want to sort them. Then I want to spread, which is pivoting. So I have a min value and a max value, and I can spread them and turn them into 2 separate columns. So let's do that here. I take the head of that weather set, and now what I have is 4 explanatory variables. Which weather station, what year, what month, what day, and then 2 aggregatable measures, max temperature and min temperature. And now I can plot the max temperatures, and I can see the range, and this is by day of month. So the maximum temperature on the 4th day of the month was just over 24 degrees Celsius. And then we go up to the top where it was about 37, somewhere on the 26th or so of the month. So that was tidyr. Let's go talk about the next set of the tidyverse, which is dplyr. See, the tidyr was just one little piece. I also showed you a little bit of dplyr, which we'll see. I also showed you just a little bit of readr, which we got to see as parsing numbers. We won't be able to see some of the other elements of the tidyverse, like lubra_date, which is a date function. So this will allow you to convert strings to dates really easily. There's also other libraries like purrr, which works really well with APIs. But all of these things are in that tidyverse library. So let's talk about dplyr. Once again, I'm loading my tidyverse data, and I also have this data set called gapminder. Gapminder is a data set that looks at data from the year 1950, I believe, 1952 to 2007, and it will include the population of a country and also the GDP of that country in each of the 5-year periods. So we sample every 5 years. Once I load the data, so I've loaded that package already. Oh, I hope I didn't mess myself up. Good, okay. I'm not on the internet right now, so it would have choked if it had to go look anything up. Anyhow, I can use the filter function to act as sort of like a where clause. Filter gapminder where the life expectancy is less than 30. And we can see that in 2 cases, Afghanistan in 1952 and Rwanda in 1992, the life expectancy was less than 30 years. Let's go the opposite way. Filter where life expectancy was greater than 81.5. And here we have a couple of Asian countries and a couple of European countries, all in the most recent data sets. And Japan was in 2002 as well. So filter acts like a where clause. Now, there is no and or, but you can get that same logic by saying a comma is an and, a pipe is an or. So let's ask for countries where the population is at least 20 million and the GDP per capita is at least 36,000 USD. We get Canada and the United States. Let's look at where population is 1.2 billion or GDP per capita is over 100,000 USD. This is all purchasing power parity normalized for, I think, $2007, but that's beyond the scope of this discussion. Anyhow, 1.2 billion, we have one country in the list. GDP per capita over 100,000, we have one country in the list. But we're able to pipe that together and get 2 separate data sets combined together. The select function, let me pick certain columns from my data set. So from gapminder, give me year and life expectancy. And it only shows you those 2 columns. So select works that way. I showed you the pipe operator already. And I can use the pipe operator to say, filter out any country that has a population under 1.2 billion. So throw those away. And then give me the country year and life expectancy of China, basically. And we see the life expectancy during that point in time. I've used mutate already to good effect, but as a quick reminder, mutate allows you to modify a data frame, to add columns or to change columns. Here I'm adding a new column called GDP. It is equal to population multiplied by GDP per capita. And when I do that, I now have a GDP of this. As a quick note, Afghanistan in 1952 is about $6 billion. That means that Bill Gates and Jeff Bezos could have bought and sold Afghanistan between them about, what, 36 times? More or less. It's a strange game they have, but whatever. I can also arrange data sets, sorting. So I've arranged by GDP. The lowest GDP turns out to be Sao Tome, and grab the top 10 using the head function. If I want to sort in descending order, I use the DESC function, descending function, and I can see that the top 10 per capita, China and Japan show up here on this set. So continuing along, new gap, I want to group it by a continent. Just like in T-SQL, I have a group by function there, I have a group by function here. And then I have a summarize function that gives me a measure. So n is just a count. So give me the count of cases by continent. And Africa has 624. This is not surprising because there are more African countries than there are in other places of the world. And Oceania is down here in 24. That is Australia and New Zealand, at least in this data set. Again, I'm not going to get into details on how we label data. I want to group by continent, and I want to summarize by the average life expectancy across the entire data set. So I use the mean function to get that. I can also get the median life expectancy or any other aggregation function that I could think of. Australia and New Zealand combined to have the highest average life expectancy in the overall data set. I can then say, I don't think it's that fair to talk about life expectancies in 1952 versus 2007. Maybe we want to filter them out and look at slices in time because that's more meaningful. During this slice of time, we see average life expectancies per continent. And then in 2007, you can see that Africa had jumped about 15 years. Oceania had jumped about 11 years. So there was some catching up in terms of average life expectancy. But all continents across the board increased. Here's a little bit more detailed data. So I have selecting certain values and I'm grouping it by continent and country. Then I'm building this new column, life expectancy delta, change in life expectancy. So it's this life expectancy minus the lag life expectancy. In other words, the previous in my group. And then I want to summarize that by finding the worst life expectancy change and getting the first value in that regard for each continent. So Rwanda had a 20-year drop in life expectancy during their genocide. Cambodia had a 9-year drop during theirs. El Salvador, Montenegro, interestingly, I guess it's not strange, it's a positive. Australia and New Zealand have never had a 5-year drop in life expectancy. The worst case was a very slight increase. So if you don't want to be depressed, you can go look on the opposite side. We could say, how about we get the largest life expectancy change? Cambodia and Rwanda had big jumps after their genocides ended. New Zealand was the biggest jump in Oceania with 2 years. So everywhere else, there were big increases, big decreases, but this has been a very consistent data set for Oceania. And single biggest gains in GDP by continent. So again, I take GDP per capita and I lag it, and I get the max. So this is all the same pattern. Asia, Kuwait had a huge jump when they found out that they have a lot of oil. Libya had a big jump. Trinidad and Tobago had a big jump. I don't get that one. I looked into it and I said I still don't get it. Not surprisingly, there's been a slow but consistent growth in Australia and New Zealand. Never any decreases, always consistently slow increases or normal increases. So in that regard, it's doing pretty well for Australia and New Zealand. So let's spend the last few minutes and look back at the data set, the Raleigh crime data set. While I do this, I am going to start running this query so that it'll be done by the time I'm done talking about this stuff. Basically, we have looked at using tidyr and dplyr on some academic examples. And now I want to tie it back to the crime data set that I had before and perform some fairly simplistic analysis to try to check data cleanliness. Nope, I did not vamp long enough. But that's okay. We'll talk about this. This is my query from incident. Oh, hey, it finished. The way that I could tell it finished is if this dot is dark colored, it means it's doing something. It is currently white, so didn't do anything. All right. From incident, join to incident code, join to incident type, I have my beat, code description type, incident date, and incident number. Have all of that data in this set. And that gives me 413,000 observations of those 6 variables. I have some basic data cleanup here where I'm changing data types, making certain values character, and others I'm making numeric. Specifically, I'm adding some new variables, incident year, month, and day, and those are integer values. I have a function here called complete cases. This is in R, and what it does is it will tell you if you have any nulls in your record. So if I just run complete cases like this, Raleigh 2014, it will give me back a true or false value for each observation. What I'm doing here is I'm saying filter out any of the records where complete cases returns false. So in other words, if I have any nulls, throw out that row. Turns out I don't have any nulls. We took care of all of that in the original data cleansing in SQL Server. So I group the data in a couple different ways using the group by and summarize functions. I want to get by year and by incident type. That way I can plot incidents by year, and what I see is fairly consistent year by year, a little bit over 40,000 incidents each year, until 2014 when there's a big drop. That's not because people stopped committing crimes in 2014. It's because I took the data in the middle of the year. So 2014 is probably not a great year for our analysis. I can skip 2014 when it comes to looking at year-by-year comparisons. Next up, do a histogram of incidents by incident type. And what we see is this is how many times an incident occurs in our data set. There's a couple that occur very frequently. There are a couple that occur pretty frequently, and there are a bunch that are less frequent. So we can see what are the most frequent incidents. Larceny and miscellaneous. We can see what's between 20 and 80,000 incidents. Assault, drugs, burglary, and everything else. Taking these, I can focus in on these particular incident types and say, I would like to put up box and whisker plots. I want to see how these change on a month-to-month basis. So filtering where incident year is less than 2014, grouping it by type year and incident month, giving me the count, and also tell me about these popular incidents where I have at least 20,000 of this incident. I have these data sets and I want to merge them together. This is the equivalent of joining. So merge using Raleigh incidents by type and month, joined to popular incidents on this column incident type. I take those two together and I can build them in a box plot. And what this shows is a few very interesting measures. The median, 75th and 25th percentiles, and then the data point that is at least, the first data point that is at least 1.5 times the interquartile range away from the median. If I scroll up and down a little bit, I also see these little dots here are outliers. There aren't many outliers in this data set. We're in a fairly consistent band, in other words. So different incident types happen pretty consistently from month to month. But if I group it by beat, I get to see a slightly different result. Here's our cutoff. Everything cuts off at 0. We can't have less than 0 incidents. But notice that we start to see some actual outliers, including these two up here that are way higher than everybody else. So something is going on in this miscellaneous category in two particular locations. And we can dig into that. We can figure out what's going on here. I'm going to spoil it for you. Turns out that those are near a mental health facility, and those were all related to mental health incidents where a police officer was involved in taking somebody to or from a mental health facility. I can also filter by other categories. So in this case, we have prostitution. And again, we have a couple of major outliers. And should you be inclined to investigate, you could figure out, well, is it that this is where all the prostitution is, or is it that this is where the police are looking for it? Serious question to which I don't have an answer. Wrapping up with QQ plots. Basically, a QQ plot, in this case, I'm asking the question, is this data normal? In the sense that it follows a normal distribution. And I'm building up a normal distribution and applying a QQ norm and QQ line. The idea is that if your data set follows this line, then it'll show you that, yeah, your data is fairly normally distributed. Our data set falls off of the line. So there's this big fall off at the end, and that tells us that no, it is not normally distributed. And in fact, I could go and look at the box plot up above and tell you this is not going to be normally distributed because you have a hard stop at 0. So if you can't have less than 0, you can't go out infinitely long on both sides, then your data is not going to be normally distributed. And here's a QQ plot. Somebody who knows a lot more about QQ plots than I do could look at that and explain the same thing that I did. That, oh, the distribution here, that you're falling off here means that you're going to end up being capped on the left-hand side. So over the course of the last hour, we've looked at a variety of data cleansing techniques. From here, you could look at data quality services or look at something that's better than that. You could integrate with external APIs. So for example, if you're looking up a postal address, or if you're looking up a UPC, or hitting Amazon and pulling back a manufacturer's number. And continuing along into other analyses, Benford's law is one of my favorites. It is around the distribution of the first digit of data sets. I have a link to that in the slides here as well. If you want to get more details, so slides, if you want the code, if you'd like additional examples, it's all at csmore.info/on/cleansing. If you have any questions at all, please feel free to reach out to me. Email address, Twitter handle. I'm also here all week. So thanks, everybody.